Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So, here is another series of problems on friction, and I hope that with these 5 problems, uh, you will develop the skills in analyzing problems on friction. So level 46, determine the range of weights W for which the 100-pound block is in equilibrium. All wheels and pulleys have negligible friction. So here is the given figure. So first, let's have the solution, and let's apply the weight W, the tension in this cable, which is equal to the tension on these cables also. Then we have the normal reaction between the 100-pound block and the inclined plane, which is denoted by NF. Then the frictional resistance. So let's superimpose the normal and the tangential axis. Then the weight 1,000 pounds, the angle 100 pounds. The angle here is 20 degrees. Then the friction, which is either way, because uh, we have to find the range of values of W. For minimum W, then impending motion of the 100 pound should be in this direction. So, and friction is equal to maximum frictional resistance is equal to coefficient of static friction 0.3 times the normal reaction. So for the solution, and friction equals zero point 0.3 of NF, and NF summation forces normal equals 0 in this free body diagram. So NF equals 100 cosine of 20 degrees, and NF is equal to 93.97 pounds. Then summation forces horizontal for minimum W, friction should be in this direction here. So W is light, so that it will be uh, pulled in this direction. So friction should be in that direction also. So summation forces tangential in this free body diagram equals 0. So we have 2t plus friction equals 100 sine of 20 degrees, where friction is zero point 0.3 of NF, and NF is 93.97. Likewise, if we draw the free body diagram of this weight here, summation forces tangential equals 0, the normal is perpendicular to the surface. So tension is equal to W cosine of 10, because this is 10 degrees. So 2 times W cosine of 10, this is tension, plus zero point 0.3 of NF, 93.97, equals the tangential component of 100 pounds, which is 100 sine of 20 degrees. So from here, we can compute the lower limit of W. So W equals 3.052 pounds. For the upper limit, motion is up the inclined plane, therefore friction is going down. So the equation would be 2t equals friction plus 100 sine of 20 degrees. So 2t equals friction plus 100 sine of 20 degrees. Friction is now in this direction, going down. So friction is zero point 0.3 of NF again. So 2 times T, which is W cosine of 10 degrees, equals zero point 0.3 of NF, and NF is equal to 93.97 plus 100 sine of 20 degrees. So solving for the maximum W, W equals 31.68 pounds. Having found W, minimum and maximum, then the range of values of weights would be 3.052 less than equal to W, and W is less than equal to 31.68 pounds. Level 47. The brake pads at C and D are pressed against the cylinder by spring BF. The coefficient of static friction between each pad and the cylinder is 0.15. So find the smallest tension in the spring that would prevent the cylinder from rotating when the clockwise couple M of 2,200 pound-inch is applied. Neglect the weights of the members. So here is the given figure. Then for the solution, let's have the free body diagram of this portion here. Free body diagram of this brake drum or cylinder. So let's have the cylinder and the other right part frame. So we will call the tension in the spring as T, the normal reaction at C as N sub C, and friction should be opposite to the applied moment. So it is going down here, and it is equal to 0.15 of N sub C as shown. So transmit it by action-reaction principle. It is upward here, and the tension is denoted by T. Then of course there will be component reactions at A, and we are not interested of that component reactions. Just place it there so that our equation would be to sum up moment about A. Then at D we have ND also. Then friction opposite to moment, so it is upward here, 0.15 of ND, downward here. Then the tension is still T, then we have reactions at E. So that's it. And of course there are reactions at the pin here. So we'll just call it vertical and horizontal. So we'll just indicate that there are component reactions there because we compute for M by summing up moments about this center so that these forces are not involved. So summation moment about A, considering this free body diagram, equals 0, clockwise positive, so T times 20 inches, then equals, that's clockwise equals counterclockwise moment, so N sub C times 8 plus 0.15 N sub C times 4. So expressing N sub C in terms of T, it is 100 over 43 of T. Then likewise, on the other side, summation moment about E equals 0. So T times 20 plus 0.15 ND times 4 equals ND times 8. Expressing ND in terms of tension, so N sub D is equal to 100 over 37 of tension. So having found NC and NT, the next step is to sum up moment about the center considering this free body diagram. So that moment is 0.15 NC times 5 inches plus 0.15 ND times 5 inches, and the moment is 2,200 pound-inch. So 2,200 pound-inch equals 0.15 NC times 5 plus 0.15 ND times 5. Factor out 0.15 times 5, which is 0.75. So 2,200 equals 0.75 quantity N sub C, which is 100 over 43T, plus N sub D, which is 100 over 37T, leaving T as the only unknown here. So from here, we can now compute the tension T. So the smallest tension T required for the system for this cylinder to about to rotate, or its rotation is prevented is equal to 583.4 pounds. Level 48, a 500 Newton concrete block is to be lifted by the pair of tongs shown. Determine the smallest allowable value of the coefficient of static friction between the block and the tongs at F and G. So here is the given figure, and here is the concrete block which weighs 500 newtons. So by symmetry, the frictional resistance, the frictional resistance should be equal to half of 500, and that is 250 newtons. And the minimum or the allowable value of the coefficient of static friction would be that friction force divided by the normal at G. But before we can compute the normal at G, we must compute the force on these links here, AB and BD. So for the solution, let's have the free body diagram. Let's call the force on these links AC and BD as F, as shown. And we have the slope given, so that summation forces vertical equals 0. So 500 newtons is equal to twice the vertical component of F. The vertical component of F is magnitude of F times vertical component of distance 75 divided by distance, which is square root of 90 square plus 75 square. So again, summation forces Y equals 0. 500 equals 2 times F. The vertical component of F is F times 75 over square root of 75 square plus 90 square, or square root of 90 square plus 75 square. So from there we can solve for F, and F is equal to 50 square root of 61 newtons. Then we draw the free body diagram of the block. We have the weight 500 newtons. So we'll call the normal reaction at F as NF, at G NG, but they are equal by symmetry. And this is 250, half of 500. That's also 250 newtons, half of 200. And that 250 is supposedly the frictional resistance between the teeth of this part and the concrete block. So let's draw the free body diagram of this portion. Transmit F. So remember, F is 50 square root of 61. If we resolve F into its components, horizontal, it is 50 square root of 61 times 90 divided by square root of distance 75 square plus 90 square, and that would be 300 newtons. So 50 square root of 61 times 90 over square root of 75 square plus 90 square, you'll get 300. The vertical component, of course, is 50 square root of 61 times 75 over square root of 75 square plus 90 square, and it is expected to be 250 newtons. Then here at E, we have vertical and horizontal component of reactions also. This distance is 90 plus 45. Horizontal distance between CE is 90 plus 45, 135 mm. And the horizontal distance between E and G is half of 315. Half of 315 is 157.5 mm. Then we'll have the friction force, which is 250 newtons. By action reaction, it is now downward. Then NG, which is rightward. And we have, of course, reaction components at E, which are not important because the objective is to sum up moments about E. So summation moment about E, or let's set up for the value of mu sub S, which is friction force over normal at G. So mu sub S equals 250 over normal at G. To solve for normal reaction at G, we sum up moments about E equals 0, counterclockwise positive. So NG times 360, then equals, these are all clockwise. So 300 times 105 mm plus 250 times 135, then plus 250 times 157.5. So from there, we can now solve Ng, and Ng is equal to 290.625 Newton. Substitute here. So mu sub S is 250 over 290.625. So the allowable value of the coefficient of static friction is equal to 0.8602. So that's it for this problem. Level 49, two blocks A and B have a weight of 10 pounds and 6 pounds respectively. They are resting on the incline for which the coefficient of static friction are mu sub A 0.15 and mu sub B equals 0.25. Determine the incline angle theta for which both blocks begin to slide. Also, find the required stretch or compression in the connecting spring for this to occur. The spring has a stiffness of 2 pounds per foot. So because the condition is the inclination theta for which both blocks will begin to slide, so that means the frictional resistance under each block would be that maximum. So 0.15 of normal at A and 0.25 normal at B respectively under blocks A and B. So for the solution, let's have the free body diagram of the entire system. Then let's superimpose the normal and the tangential axis so that the angle that the weights make with the normal is theta. So we have 10 pounds and the normal here is NA, and that's theta. Then friction should be up to the right. Then at B, 6 pounds, angle theta with the normal. Then normal reaction at B, NB. Then friction, we have 0.15 NA, then up to the right 0.25 of NB as shown. So for NA, summation forces normal equals 0 considering this FBD. So NA is 10 cosine of theta from the figure, while NB is 6 cosine theta summation forces normal considering this free body diagram at B. Then summation forces tangential equals 0. We have 0.15 NA plus 0.25 NB equals 10 sine of theta plus 6 sine of theta. So substitute the value of NA. So 0.15 times 10 cosine theta plus 0.25 times 6 cosine theta. This is 0.25 by the way. Then equals 10 plus 6 is 16 sine theta. So 1.5, this is another 1.5. So 3 cosine theta equals 16 sine of theta. So that means tangent theta is 3 over 16. And from there, we can solve theta arctan of 3 over 16, and it is equal to 10.62 degrees. Then for the required stretch or compression, let's draw the free body diagram of this part. The tension is equal to 2 times delta S. So force is spring constant times change in displacement. So let's call the change in displacement as delta S, stretching, that's the expected value. So summation forces tangential equals 0. So F plus 0.15 NA equals 10 sine of theta, where F is 2 delta S, then 0.15 of NA, which is 10 cosine of 10.62 degrees, equals 10 sine of 10.62 degrees. So leaving delta S as the only unknown in this equation, so we can now solve delta S in foot 0.1843 of a foot. Then level 50, determine the distance to which the 90 kilogram painter can climb without causing the 4-meter ladder to slip at its lower end A. the top of the 15-kilogram ladder has a small roller, and at the ground, the coefficient of static friction is 0.25. The mass center of the painter is directly above her feet. So, because the top is roller, then there is only normal reaction, no frictional resistance at the top end of the ladder. So for the solution, let's have applied the weight above her feet, shown. Then take note that the weight of the ladder is 15 g, and the weight of the painter is 90 g. So we will, if we denote the weight of the painter as W, then we can express the weight of the ladder in terms of W. So weight of ladder is 15 g over 90 g of W. So the weight of the ladder as a fraction of the weight of the painter is W over 6. And let's apply it. It acts at the center, 2 meters from either end of the ladder, as shown. We will call this angle theta here, so that the moment arm of the weight of the ladder from A is 2 cosine of theta, as shown, where this is theta. And for the weight of the painter, it is S cosine of theta. So this distance is 4 sine of theta, this vertical distance between A and B, and the horizontal distance between the weight. Let's have normal at A, friction, which is to the right, 0.25 of Na, then normal reaction at B and B. So, of course, summation forces vertical equals 0 or normal, Na equals W plus W over 6, and Na therefore is 7 over 6 of W. Then take note that 0.25 of Na is equal to Nb if we sum up forces horizontal. So 0.25 of Na equals Nb. So 0.25 of 7 over 6W equals Nb. So that means Nb is equal to 7 over 24W. So the last part is we sum up moments about A equals 0. So we have Na, Nb. So theta is inverse cosine, by the way, of 1.5 over 4 from this figure here. So theta is equal to 67.976 degrees. Then summation moment about A equals 0. So we have W times S cosine of theta, which is 67.976, the moment arm of the W, plus W over 6 times 2 cosine theta, this is 2 cosine theta, then equals NB, which is 7 over 24W, and the moment arm is 4 sine of theta. So 4 sine 67.976. Cancel out W, and the only unknown left is S. So from there, we can solve for S, and S is equal to 2.551 meters. So that's it.